Hmm. Right, I think we'll make a start. Welcome to this evening's webinar. I'm Rob MacDonald. I will be the host for this evening's Mersey and Western Cheshire Energy and Environment Group webinar. The Mersey and Western Cheshire local network is based on the northwest of England and includes the Isle of Man. The local network has a number of specialist groups, and one of those is the Energy Environment Group. Darren, could you click the next slide? Thank you. Today's webinar is entitled Grid Stability, Maintaining Grid Stability with Changes in Electricity Generation and Usage, and will be presented by Mr. Darren Jones, Technology Manager, Hitachi ABB Power Grids. Ensuring grid stability with the changes in electricity generation, storage and use is a challenge not only for the UK electricity network, but for electricity grids across the world. Next slide, please, Darren. The programme for the webinar will be in three parts: an introduction to the Mersey and Western Cheshire Energy Network and Energy Group, a presentation by Darren for about 40 minutes, and a question and answer session after that. The plan is that we'll close the webinar after about an hour. So if there's some questions that have not been answered, we will answer them by email after the webinar. Please please submit your questions using the Q&A box, not the chat box, especially if you use the Q&A box, and we'll take the questions at the end. The webinar will be available on the Mersey and Western Cheshire Local Network's YouTube channel in about a week's time, if you search for the channel on YouTube using IET Mersey and Western Cheshire. If you'd like a CPD sticker for attending this evening's webinar, I'll post the details as is in the chat box, and in fact I've already done that. So if you look in the chat box, there's some information about CPD certificates and contacting us and so on. Next slide, please, Darren. You can go back one. I think we had one ahead of me there, Darren. So the Energy and Environment Group is one of a number of specialist groups in the local network. The Energy and Environment Group members are focused on issues for providing energy whilst protecting and improving the environment by organising free-to-attend events and technical visits. Because of the impact of COVID-19, we're using Zoom webinars at present. The group's focus is deliberately wide-ranging to embrace all aspects of the provision, distribution, usage of energy and the associated environmental issues. If you've got any proposals for a future event that fits into the group's focus, I'd be pleased to hear from you. Next slide, please, Darren. So the local network organises lectures and seminars, including webinars, of course. We do workshops. We do recognition events to recognise new chartered engineers, fellows, Eng-Techs, incorporated engineers. We organise group meetings. We try to organise an annual dinner when we're able, and we publish an events newsletter twice per year. Next slide, please, Darren. It would be great if you could come along to one of our free-to-attend events, join one of our groups, involve your organisation. We're always looking for topics for lectures, webinars and technical visits. If you'd like to contact me, my email address is on the screen. I would now like to hand over to Darren to start his presentation. Darren?
Thanks, Bob. Thanks for that great introduction. Hope you can see and hear me okay, Bob. Can you just confirm before we start?
Yes, I can hear you clearly.
That's perfect. Thanks everyone. Really great to have you on board on the webinar tonight on what's a rather dark and miserable October evening in the north, talking to you here from the northwest of England. So a real warm welcome. And one thing I ought to mention just before we get into the details is I noticed there was a mistake in the introduction. I'm actually with Hitachi Energy now, Hitachi ABB Power Grids. So we didn't quite update all the slides in a timely manner, let's say, anyway, because my organisation recently changed from ABB to Hitachi Energy, but that change actually only happened last week. So still somewhat a work in progress to make sure that we're all branded correctly. So anyway, just a very brief introduction to me. Once again, thanks for joining everybody. I'm Darren Jones, Technology Manager, Hitachi Energy. I've been with Hitachi Energy about just over 3 years now. Before I joined Hitachi, I was the Innovation Manager. I spent about 10 years at Electricity North West, which is the distribution network owner and operator in the northwest of England. I was the Innovation Manager there for a number of years. I'm responsible for a number of different aspects of Electricity North West innovation activities. Before Electricity North West, I spent a few years at a consultancy in the northwest of England, EA Technology, that some people on the call might know, around one of the substation research groups for a few years. And before EA Technology, my first job in my professional engineering career was with a now defunct organisation called ABB Power T&D, and they were based over in Ellesmere Port. So that's me anyway. Once again, thanks for making time to come and listen to us tonight. What we wanted to talk about is grid stability and what the change that's being driven by the energy transition might mean for grid stability in the future. We wanted to talk just briefly through how the UK energy system has evolved over the last 120 years and how we've ended up where we are today with a highly reliable and resilient system that we all in the UK enjoy the benefits of. We'll talk about how the system is kept stable today. I want to touch on some of the global drive for net zero and the electrification of loads and the increase in generation and the move to renewable generation. Bob and I were just talking before before we started the session to say, I'm sure again a number of people will be interested on this call would have seen a raft of government publications today around net zero objectives and how they believe they're going to achieve net zero. So I hope you'll forgive me that some of these slides might be somewhat out of date based on today's publications, but it's really a factor and a feature of the kind of role I have, that it really is a full-time job to try and keep up with these changes now in government moves. So anyway, as we look at the increasing share of renewable energy generation on our electricity network, we want to talk about the characteristics of those renewable energy generators and how they're vastly different to the centralised energy generation that's been used to drive the system again to achieve the levels of reliability and resilience that we enjoy today. And then also finally to include just some of the technology solutions that we have available to us to keep the grid stable and secure, and what that might mean for the future and some of the ways that the electricity network might need to evolve in the future. So by way of an introduction, the UK electricity system, it's began life around 120 years ago, and what you can see on the left-hand side of the slide here is just some of it's a non-comprehensive, non-exhaustive list of some of the legislation that's been enacted by various UK governments over the last 100 years to foster and encourage the development of the electricity system in the UK. Started life around the turn of the last century, and that was really the growth and the emergence of small, independently owned electricity distribution networks. They were effectively islanded networks. They had their own small generation and a small number of connected customers, and that was really driven by the desire to move away from gas as a source of domestic lighting, because obviously there's, it's not the best thing to be burning town gas for lighting in homes. So some entrepreneurs at the time saw the opportunity to begin to develop their own privately owned electricity networks. They moved into the 20s and 30s, and that was a time when these independent electricity networks began to grow, began to interconnect with each other. It was a time of great innovation in the UK, as these electricity networks began to grow and be interconnected, as I say. It was a time when the manufacturers of electrical equipment, those organisations begin to grow to serve these greater needs. And also as those networks interconnected, it's one of the reasons now we have some rather odd voltages in the UK, 240 volts for low voltage systems and 11,000 volts for low voltage distribution systems. And that was really as a compromise voltage to allow those different networks to interconnect with the least impact as they were all brought together and standardised. We then went into the 1920s and 30s. Then we had the emergence of the transmission system in the UK, and that was then really to allow the benefits of scaling up energy generation, all coal-fired energy generation at that time, as I guess everyone would appreciate. But in the 30s and 40s, we began to see a much more interconnected electricity system. Then into the 40s, 50s was the time of nationalisation. That was when the government took ownership of these small, independently owned electricity networks, and that was really to accelerate and drive investment in the electricity network. Of course, we all understand that reliable and resilient electricity networks are a real driver of economic growth and social health. So there was privatisation in the 1940s and 50s, and that again was to encourage investment, to train workforce. So significant apprentice schemes started around that time, and that was really to get the workforce fit to expand and complete what has become the electricity network. The 1960s and 70s was the time of rural electrification, and that was building out the networks to reach more rural and isolated communities. And again, that was to make sure everyone on the islands of the United Kingdom had access to secure and reliable electrical energy, and again as a driver of economic and social health. So we then went into the 80s and 90s, and that was a time of privatisation. That was when the electricity network was then broken up and sold off to private ownership. That was to drive efficiency, increase investment in the electricity network, and to make sure we really had an industry that was fit for the future. What I've tried to include is just a couple of outline maps here. I mean, these are all publicly available information. You can see the map on the right there shows the location of the major energy producers in the UK. That's kind of gas, coal, oil. Also notable in the top in Scotland, there's a huge amount of hydro energy generation in Scotland. That's obviously to take advantage of some of the geography they have up there. So the map on the right kind of shows where energy is produced in the UK today. Sorry, the map on the left. The map on the right shows the infrastructure itself, and as everyone can see, it's absolutely ubiquitous across the whole of the islands of the United Kingdom. The map on the right also shows some of the new offshore wind farms that we're seeing now off the coast of East Anglia. I think the latest one was Dogger Bank A and B. I think that's built and commissioned. Dogger Bank C has just been signed off, I believe. So we have around 10 gigawatts of offshore wind now, which has gone from 0 standing start in the last 10 years. Also worth pointing out are the interconnectors that we have in the UK now over to mainland Europe. On the top right there, you can see the very recently commissioned interconnector over to Europe. And I think I can say that's the largest subsea, the longest subsea interconnector in the world today, I believe. And also the interconnectors down into France. They've been in the news recently, as I'm sure at least some people will be aware. And interconnectors, again, are just to give us access here in the UK to the clean, reliable, zero carbon sources of energy that we can get access to in Europe. So if that's the electricity system, you know, what kind of technical engineering services are required to ensure that the grid remains secure and stable and resilient under all the different loading, the dynamic loading conditions that are experienced on a day-to-day basis. The four primary technical parameters that are managed are highlighted here on this slide. And it also gives a snapshot around the edges of some of the technology that's used to manage those technical parameters. But I certainly, in the interest of time, I certainly don't intend to go through that in too much detail now. The main things to bring out of this on the right-hand side, we have system strength and voltage control. The electricity network owners and operators have a statutory legal duty to keep voltage within certain limits. And that's to make sure that the equipment that's connected to the network can function correctly. If voltage is too high, then it could cause damage to customers' connected equipment. And the converse is true, voltage is too low. That can also cause maloperation. So voltage is controlled and managed by making sure we have the right level of system strength, which is effectively a measure of the impedance of the network. So the network is designed to have a certain impedance to make sure voltage is managed. Voltage control is more difficult on long overhead rural networks, typically, where we have long units, and voltage will tend to drop per unit length of the feeder. So there's great emphasis on managing and controlling voltages. by maintaining and managing system strength. Just like the network companies have a mandatory duty, a statutory duty to measure voltage, like the same with frequency, and for the same reason that if frequency isn't managed, we have a 50 hertz AC system in the UK, as I'm sure most people will know. But if that frequency isn't managed and kept within its limits, then again, can potentially cause damage to customers' connected equipment. So one of the things that's used to manage frequency in this dynamic network we have with dynamic power flows is inertia. And we will talk about that a bit later on in the presentation, because this really is the subject of the slides today, is the fact that we're losing inertia from the system. Unlike system strength impedance, which is a physical feature of the way the assets are connected together, inertia is a property that's delivered into the network by virtue of the way it's designed, having large centralized power stations, and its inertia is one of the things that's used to manage frequency and keep that within the right limits. So next slide, to the heart of the matter, and people may know this generally anyway, but this is how the system is balanced today. We do have access to energy storage on the electricity network, but it's not particularly prevalent at the moment. I mean, that may change in the future. What that means is the National Grid have a statutory obligation to balance generation and demand. And as the slide tries to make really clear here, if there's less generation than demand, that leads to frequency falling below the 50 hertz level and outside its statutory limit. In that circumstance, National Grid either need to increase generation or decrease demand. And again, the converse is true. If there isn't sufficient demand to meet the generation that's available, and that causes frequency to rise. And again, the action needed to be taken is either to decrease generation or increase demand. And this is real live 24/7 network balancing that happens in every control room up and down the UK. Every electricity network control room in the UK has a large clock on the wall with a readout of the 50 hertz frequency. And it's 24/7 job to maintain that balance between generation and demand, to maintain frequency. And one point that I did want to bring out on the last slide is that frequency is actually common across the entire network, whereas voltage levels are quite local. So frequency is the way that the network is managed. The last, I think I can say, the last major system event we had in the UK was in August 2019 down in the southeast. That was when there was a lightning strike to a couple of overhead lines that were connecting some of the offshore wind out on the east coast. So I think the lightning strike took the overhead line out, which meant that the wind farms were disconnected from the system. I understand, I mean, again, there's plenty of reports available if anybody really wants the detail, but there was also a case that some of the other standby generators that were supposed to connect to the system and meet the shortfall in generation failed to activate or failed to operate at that time. That then caused frequency to fall effectively, because that was the case where we didn't have enough generation to meet the demand that was connected. Once that frequency began to fall, that then led to the operation of low frequency demand disconnect schemes on the connected distribution systems. So I know UK power networks, they had quite a significant amount of their demand disconnected from the network at that time. And again, that was demand disconnection to make sure that the balance could be brought back to the available generation. We didn't have the ultimate risk is a cascade failure and a widespread system blackout. So the system worked perfectly at that time, and the balance was maintained. And even though some people were off supply, which of course is not the best experience, they managed through the means that we accept, the way it's understood this happens, they managed to keep system stability and keep the network online. So that's the job that needs to happen, balancing the grid between generation and demand. What we have here is, I mean, again, this is quite a wordy slide, and I don't intend to go into this in any great detail, but what we want to highlight here is how the system is actually balanced through the ancillary and the balancing and ancillary market design. As the slide says, National Grid have a statutory obligation, a legal duty, to keep the system stable and keep the frequency limits within 1% of the 50 hertz. And this is constantly changing. So the way energy is kept stable is that National Grid have access to these balancing and ancillary markets. And that's basically just, they have a forward view of demand and what demand may be at any one time. So National Grid can contracts with generators to make sure that demand can be met. As we get closer to real time, we're then into the balancing and ancillary markets, where National Grid basically have reserve power, the reserve generation or reserve demand, that they can do this fine tuning and moment by moment balancing of the energy network. And they have a huge range of tools and techniques that they're available. We're perhaps just bringing out things like short-term operating reserve. I mean, we're all familiar in the UK when we have big sporting events and at half time or at breaks in those big TV events, you know, lots of people rush out to make a cup of tea. And then that causes a very short but quite a high magnitude spike of demand. National Grid have things at their disposal like the Norway pumped storage hydro plant in North Wales. They can basically tip huge amounts of energy into the system really quickly. So National Grid literally have people sat around watching these sporting events, watching the response of the system, on the phone to get ready to tell people to push a button to release that energy from things like that short-term operating reserve, literally on a moment's notice. So these are the means that they keep the network stable. So the thing I really wanted to bring out, and the point that I hope I've made at least partially well, is that the UK electricity system is a very mature and well understood system. It's grown up over a long time. The engineering principles of how the system operates and kept stable are very well understood. And there's people who are absolutely expert at keeping the system stable. They have these very mature and well understood commercial mechanisms. Excuse me. They are very mature and well understood commercial mechanisms that have been developed over many years, and the way the system is kept stable and resilient and secure today has evolved over time to give us this huge and high levels of reliability that we enjoy in the UK in terms of the energy system. I think it's around kind of 98.9% reliability in terms of energy supply in the UK. So that hasn't happened by accident. It's happened by people understanding and developing these markets and these tools and techniques over a long time. So that now brings us to the future and the changing picture and what we're likely to see in the future. And again, a big part of this presentation is to try and explain a flavour of how we've managed electricity systems in the past may not be quite so suitable for the way they're going to look in the future. So what we can see, we can all see this, we all read the news, I'm sure, we're all familiar. And again, I touch on the publications today, the net zero plans the government published today. So, I mean, you'd have to be living on a desert island to not understand there's a huge global move towards net zero, towards decarbonisation, energy and energy generation. Right back to the 1990s and the Kyoto agreements, when they were made, it was clear at that time it was energy generation, transportation and heating were the big sources of carbon emissions. So energy generation, electrical energy generation has gone through this huge path of decarbonisation over the last 10 or even 20 years. So we can all see that shift towards electrification. That's happening on a global scale. I think the latest projections you hear, but again, this is probably out of date by now. It's estimated the UK is going to double its electricity demand in the next 20 years. Again, we're all aware, I'm sure, at least broadly, of the plans to install 40 gigawatts of offshore wind by 2030. We're, as an organisation, Hitachi Energy, we're quite close to some of the academics down in Imperial College down in London. Again, if you excuse me. Not to the academic study that those folks are carrying out there now suggests that we may need 100 or even 120 gigawatts of offshore wind to meet the future electrification. So what this chart is trying to show is that you see at the bottom here, there's a number of different organisations that carry out really detailed study and do some really detailed analysis of government policy, both how it's enacted today and how it's likely to shift in the future. If they look at those global trends, and all of these different researchers are all saying the same thing. that we're on a irreversible shift towards electrification of energy demand. And they all say renewable energy is going to become the dominant energy source. The cost of renewable energy, the cost of wind and solar has fallen in ways that no one could have imagined even 10 years ago. Renewable energy is now the cheapest form of energy generation, I believe. Again, you can appreciate the time it takes to bring a solar park on farm compared to the time it takes to bring a nuclear power station online. Everyone can understand that why renewable energy is now and will remain the cheapest form of energy. So again, what we say here, what we can see here, not to dwell on this too much, but there's some of the mega trends that we're seeing now across the world, and we're seeing at the moment the amount of energy that's generated by oil and natural gas and coal, and we're seeing in the future how those mega trends are moving towards more wind and solar, hydro, nuclear. And we should see coal disappear off the network, I believe, in the next 10 years. Although, as again, it's been in the press quite widely reported that we have seen some coal generation used in the UK over the last couple of weeks and months, and that's to meet this wind-free period that we've been experiencing. But the coal that's been used over the last few months has been a tiny fraction of the amount of energy that's produced. People may know again that there's a number of really good websites if anyone's really interested in the generation mix. The National ESO have a really good website, and that will show you the instantaneous energy mix at any given time. And if anyone's suitably interested, I can recommend that there's some interesting information on those websites. But what we're seeing here is there's a shift to electrification of energy demand. That in the UK we experience it, it's transport and heating. We can all see those trends. But there's a huge amount of analysis that's actually going on, happening at the moment to understand exactly what that means. Also, I guess if we're talking about energy, we have to mention hydrogen as well. It's not entirely clear at the moment what part hydrogen is going to play in the energy mix, but we know it will be playing a part, and there's a significant investment at the moment going into hydrogen as a source of energy. So if that's the global picture, what does that actually mean for the UK? Well, we can see that energy demand in the UK is actually falling significantly since 2010, and of course this has been impacted by COVID, and everyone would understand that over the last 18 months. Up until around 2010, energy demand in the UK, I believe, generally always used to increase by about 1% a year. The question for network planners was only ever where would that increase in demand take place, and where would the new networks be, and where would the load growth be. But since energy networks started up until about 2010, energy use rose year on year by around 1%. Around 2010, around the year 2000, what we began to see around 2010 was the introduction of low energy light bulbs, as we began to move away from incandescent lighting for domestic lighting down to low energy LEDs. We were replacing 80, 100 watt light bulbs with 3 and 5 watt LEDs, and that's had a huge impact on energy demand in the UK. So, and also, of course, as more domestic devices and white goods have become more energy efficient, TVs are a lot more energy efficient than they were some of the newer style, newer technology. And so we can see the short-term trend where energy use is actually reducing in the UK now. And again, we can see fossil fuel energy generation as the graph tries to bring out the fossil fuel energy generation down by a huge amount as offshore wind has grown. I mentioned about 10 gigawatts offshore wind from a standing start over the last 10 years, and also several gigawatts of solar. So we can almost see now one of the new problems National Grid are now having to manage it is low demand in the day when we have significant amounts of solar energy generation. I mean, anyone can walk around any town or city in the UK now and see the amounts of domestic solar that's been connected on people's roofs, been installed on people's roofs. So it shouldn't come as a surprise to anyone to see the effect that is actually having on the amount of energy that we use. And also, as the slide says, renewable energy generation is up significantly. What I've tried to show here, I mean, again, this is one of the ways I may have been caught out on this presentation, excuse me, This was a document that was published at the end of last year. It was a really interesting document for those who follow these things closely. This was the Department of Business, Energy, Industrial Strategy, and they were looking at the pathways to 2050 and how this net zero 2050 could be achieved. There's many different pathways, of course, as everyone could understand. There's many different ways it could be done. But of course, the government have the responsibility for making sure taxpayers' money is used most effectively and most efficiently. So what the government need to do and what they've begun to do today, and I believe that from early reading there are still some gaps in there, but the government responsibility is to to enact the policy, and we touched on that. We saw that on some of the slides earlier on. There's been a long history of government policy that dictates the way electricity networks evolve and the way they're funded over time. So it's the government's role now is to come up with the policies that is going to let this investment flow. I mean, we've got some great plans and some great strategies, but it's actually policy that we need now. And this document looks at a range of different pathways and a range of different policy options to achieve this 2050 net zero system. Why it's simply worth mentioning because of these two facts here, so that whatever those pathways, whatever pathway we take towards 2050 net zero, they are going to involve significant amounts of wind and solar for the reasons that I've already highlighted in terms of the cost of wind and solar now. I believe solar wind will at least quadruple by 2050. And I suspect, as I say, when you speak to some of the academics, you know, they believe that that figure may even be quite conservative by the time we reach 2050 if we are to achieve the net zero targets that we have. So I hope that paints the picture of how the energy system is changing now and how we see more and more renewable energy on the system and why the system's changing and how it's going to look in the future. What that brings us to then is, excuse me again, if we do have ever more increasing penetration of renewable energy generation on the network, that brings with it some challenges. Anyone can understand and anyone will know, you know, it's a basic fact that renewable energy generation is not predictable in the same way that fossil fuel energy generation is. You know, large centrally based energy generators that can be manipulated and can operate in the commercial balancing and ancillary markets are absolutely not the same as renewable energy sources, wind, solar, and some of the other weird and wonderful ways that are now beginning to see people generating and storing energy. These renewable energy generators just do not act like fossil fuel generators. Again, I guess it's self-evident to everyone to say that wind turbines do not spin at 50 hertz. Those wind turbines are variable. The speed they operate at and rotate at are variable in nature, depending on wind strength, different time of day, different time of year. So one of the fundamental differences that we want to bring out for the purpose of this discussion is lots of those wind turbines, and again I hesitate to try and I can't say all and be too general. We need to, you know, understand that there are a number of different flavors and different types of technology, but I think we can say generally that wind turbines are connected and synchronized onto the transmission system through power electronic converters. They take the input half of the power electronic converter, takes the input, takes the rotation of the turbine, whatever speed that is. And the power electronic converter takes that variable output and converts it to a DC voltage. The DC voltage then drives the output of the power electronic converter and produces this 50 hertz output that is matched and synchronized to the grid. Now again, not all, it's important to say, but many power electronic converters that are adopted on wind turbines today use what's called phase lock loops. So they essentially take a 50 hertz reference signal from the transmission system, and then they use that 50 hertz reference system to drive the output power electronics to match the output of the wind turbine with the, or to synchronize and match the output of the wind turbine with the grid. Some of the newer wind turbines do offer what they call fault ride through capability, which means that if there's a disturbance on the network or some kind of fault or system event, they will stay connected. By and large, the majority of the old power electronic converter connected wind turbines with this phase lock loop system They will simply disconnect themselves at the first sign of a network fault or some kind of disturbance or some kind of event on the network. And the key difference now, and this is again trying to describe the thread of the presentation, by and large, most of the renewable energy that's connected to the UK system will not provide inertia that we touched on earlier on, which is absolutely a key fundamental technical requirement to allow the national grid to maintain the frequency of the system. So this is what was happening, and you can see the map on the right hand side of the screen. I think that was taken from one of the DEC websites. They have a website of all the either in-flight or consented or built renewable energy projects in the UK, around 7,000 or 8,000 of those renewable energy generators now in the UK of all different flavours and types and sizes. And how we're moving away from that large fossil fueled energy generation to this distributed energy system now. But very few of those renewable energy generators will provide this property of inertia that we touched on earlier and talked briefly about. Inertia is what we need to make sure that frequency is maintained in the event of system faults. So what actually is inertia? A simple dictionary definition of inertia, as anyone will be able to tell us. Inertia is just the resistance of any physical object, the resistance of the change of its state of motion and position. If an object is in motion or is at rest, it will remain at rest or in motion unless acted on by some kind of external force. So really important point, the definition of inertia, which is why it's highlighted on the slide here. The inertia is just the term given to the store of kinetic energy in the rotating mass of those thermally driven generators. It's an absolutely fundamental feature of the way those large power producers operate, the way they've always operated on the system. It's just absolutely key part. The inertia that's been provided essentially for free, just by virtue of the fact of the design of these large power stations. The system has taken the benefit of having free inertia just by virtue of the way it's designed. And this is what we're now losing with this move away from fossil fuel generation over to renewable energy generation. And it's the inertia where the store, as the slide says, the store of kinetic energy in the rotating mass of that generator turbine. So what we're experiencing is a fundamental shift in the way the system is going to be operated in the future. As I tried to say at the later points in the slide, inertia drives short circuit currents. The fact that we have that energy in the system, when there is a system event or some kind of network event or a fault, the inertia that's in the system continues to drive energy into the system. No matter what the network is actually doing, the inertia continues to drive energy into the system in the form of a short circuit current. And it's the short circuit current, this energy that's driven into the network in the event of a fault or a system event, that drives network protection systems, which disconnects the faulted part of the network from the healthy part again. So as I'm saying here, so avoiding system failures and avoiding cascade failures. What we can see, we have here the equations that describe inertia and the inertia constant. I mean, in some ways, inertia constant is just a mathematical concept. It doesn't actually exist in real life. It's just a mathematical concept that's used by network designers for them to be able to design networks successfully. And again, most people, I guess, will recognize this equation on the top. It's just half the mass times the velocity squared. In its rotational form. So it's just simply the inertia constant is just simply the store of kinetic energy divided by the system power, and that inertia is used as a fundamental design parameter when people are designing new networks to make sure that they remain stable. Another key part of inertia that we can see here, another way that inertia is used on the system is the amount of inertia drives this change in frequency. Or actually, the more inertia we have, the less of a change in frequency. The change in frequency and the change of time, the rate of change of frequency. The more inertia we have on the system, it simply follows that the more inertia we have on the system, the more kinetic energy we have, the more fault current that flows. It helps to arrest the change in frequency. As we go back to what we talked about earlier, if we have an imbalance in generation and demand, the more inertia that we have on the system arrests the rate of change of frequency with time. So basically it gives the national grid, the system owner or the operator, the time to take corrective action. This slide, or the next slide now, this is kind of the anatomy of a system event. And there's any control engineers amongst us tonight, you probably recognise this as a kind of system response diagram. There's 3 salient points on this graph. We can see initially this is literally the rate of change of frequency. We can see how frequency changes with time, and that was described on the previous slide, dependent on the amount of inertia. UK system is designed to have enough inertia to last for 10 seconds, and it's that 10 seconds when the I mentioned previously the balancing and ancillary markets, some of the commercial arrangements for fast frequency response, which is typically provided by battery energy storage systems now. This 10-second gap here when the system frequency begins to fall is designed to make sure it doesn't continue to fall, and National Grid here at this point, as we reach here, the second salient point on this graph is called the frequency nadir, which is the lowest point that the frequency will reach in the event of a system event. So the system is designed to have enough inertia for 10 seconds to allow the secondary measures, fast frequency response, backup generation, allow them to operate and allow them to arrest this fall in frequency, and the frequency then is brought back up. And we have the third point of this graph is the steady state frequency there, which is the point that we then need to recover the system from. So what we can see here, it follows naturally from the previous equations that we looked at. The less inertia that we have on the system, the greater the rate of change of frequency, and the greater the frequency nadir will be, which means it's more expensive or more difficult for the national grid to then bring the system back to a stable state. So these key parameters are what is managing and describing the system response to these major events, like what I mentioned previously, the loss of a large wind farm, the loss of a significant amount of in-feed generation. What we have on the left is excuse me, some analysis that we did at Hitachi Energy with some of our colleagues over in NSOE in Europe, and they're just an engineering technical research organisation, not dissimilar to Seagray or SARED, but we've done quite a bit of research with the folks over at NSOE, and that's looking at the implications for ever more increasing penetration of renewable energy as a proportion of the amount of load that is being served. And what we can see, I mean, it's clear again, it follows kind of completely follows from the previous description of those equations that we use, that the more renewable energy that we have, the less inertia that we have, the less the inertia constant that we have. As the inertia constant reduces and the system becomes more unstable, and we have these faster dynamics of these low inertia systems, that we may need to use other means and other methods to try and control the system. So I hope that gives at least a flavour of what inertia is and why it's important and how it helps to control frequency. But as we move towards a greater penetration of renewable energy systems, we do have some technology solutions that we can bring to bear on the energy network. Excuse me. Things like synchronous condensers, and again, people on the call may be more or less familiar with some of these technology solutions. These are the technology solutions that we can adopt to make sure the system can run successfully with those very high penetrations of renewable energy. Synchronous condensers are basically just a large electric motor inside this box. There's a large electric motor, and synchronous condensers are often come with a flywheel. And it's that big flywheel, the physical mass of the flywheel connected to the synchronous condenser that provides this inertia, this rotational mass that's used to use the kinetic energy stored in that rotational mass to inject into the system in times of fault. Synchronous condensers are driven by what's called a pony motor here. You might see there's a small motor that drives this larger motor up. They don't generate any active power, but synchronous condensers can manipulate power factor. The stator and rotor circuits can be either over or under excited to produce either leading or lagging power factor. So as well as inertia, they can provide reactive power services onto the grid. But synchronous condensers are expensive, and it's old and tried and trusted technology. They've been around a long time, but I think it's fair to say they're quite high maintenance because it's a rotating machine. So I guess anyone can understand that big rotating machines do take quite a bit of maintenance. They are maintenance intensive and quite expensive to operate. Some of the new technology that we're now seeing used to provide inertia onto the system are things like large battery energy storage systems. This was a system that Hitachi installed down in Australia. That was a place in Australia, a location where they had a huge amount of renewable energy resource, a huge amount of wind. This area in the southeast, I think, of Australia was fed by a couple of very long overhead lines. And there also wasn't many customers down there. So the choice that the Australian transmission operator had was either to reinforce and expand the overhead line, which is a really expensive thing to do, or to install a battery energy storage system. What we found was that because the cost of battery energy storage has fallen just to a fraction of a percent of what it was even 10 years ago, and that is on that trend is set to continue. That battery energy storage is becoming ever cheaper. So this then made this battery energy storage system a viable solution to some of the problems that the Australian network operator was having. What the battery energy storage system could do, as well as providing inertia onto the system, what we call virtual inertia, which is the quite clever power electronics that can be programmed to feed in some really clever algorithms that can use the energy store within the battery system to use that as a form of synthetic inertia. Which meant that the electricity transmission owner did not have to reinforce the overhead line. What we began to see, though, and it's kind of worth pointing out with the battery energy storage system, that this overhead line that fed this population down the southwest of Australia was prone to lightning strikes. So 2 or 3 times a year, the population of these towns and cities were used to being off supply for a period of time. What the battery energy storage system can do is when the overhead line is lost, they can basically support the local demand so they can keep those customers on supply. So what we see now, unlike the synchronous condenser, which basically does one job and it does it very well, let's be clear about that. What we can see with battery energy storage systems is they offer a greater range of solutions. And we have this concept, and again, I'm sure most people are familiar with revenue stacking, which means we can invest in one asset that can then perform multiple functions according to the needs around it. And they bring with a huge amount of flexibility. So we can see then that the cost benefits of these types of investments become actually a lot more attractive for the owners and operators of those networks. So we can see a real trend towards battery energy storage systems. We also have other devices that we can use for power conditioning and providing forms of inertia onto the system, things like StatComs. Slightly confusing terminology, I think, that we like to use in our industry. StatCom is short for a static compensator, and it almost does the same job as a synchronous condenser, yet it's static. It doesn't rotate. It's a static device. So StatComs are often used at HVDC systems, and they're power conditioners basically, so they can take power and they can deliver it in various forms by altering phase angles and phase shifting, and they can provide a form of synthetic inertia onto transmission systems. And again, we're seeing that there's a range of devices in what we call our flexible AC transmission system family of devices, power electronic devices. That's a market that's certainly increasing across the globe now as people are looking at some technology solutions, again, to make sure, as we've covered in some detail, the grids and networks remain stable in the face of this high penetration of renewable energy. I think finally, also on some of the technology solutions, you have to talk about data as well. It's not all about physical technology. There's great opportunities with data now. No presentation, I think, is complete now in 2021 without mentioning artificial intelligence and machine learning. But we're actually seeing now that what some really clever people are beginning to do now is interface with different data systems. One of the challenges we've had in the industry over the past 10, 20 years, even certainly I've been involved in innovation, is that we have lots of data that describes the networks and describes the system. But lots of this data is in different databases and different formats and in different silos. What we're now being able to see is some really clever people able to develop means of interrogating different databases, not just the databases that describe the energy networks, but also things like meteorological databases. All this data is now coming online. So there's some really, really clever and innovative work with organisations looking at this data now, creating new data systems, looking at forecasting, you know, how and where does cloud appear? What are the meteorological conditions that will dictate what direction the wind's coming from? How do these global weather patterns and global systems affect what happens locally in terms of the outputs from renewable energy generation? So as I mentioned in the previous slide, that renewable energy generation was unpredictable. It's becoming less so, as our ability to forecast what's happening with those renewable energy sources is growing all the time. So it's important to say it's not just all about technology solutions. There's also a huge opportunity with data and forecasting as well. So as we move forward now onto flexibility, we have to talk about flexibility because, again, there's other ways. We have the problems of lack of inertia. We have the penetration of renewable energy system, as well as some of the technology solutions that we also have. We have other means as well to manage grid stability, and this is by flexibility on distribution networks. National Grid have participated in flexibility markets for many years, as I said previously, but that's really only open to large energy users or to large demand users. What we're seeing now more in 2018, as the slide says here, that all the distribution companies agreed that they would, rather than just build new network when they needed new infrastructure, need to meet new demand, they would understand what flexibility might be available through their domestic customers. Not just simply means paying customers to move demand, to switch demand off, to increase demand according to certain times of day. So again, the very early slide, when we look at the balance between generation and demand, and so far they've all been measures taken on the generation side. Well, there's an equal opportunity to take measures on the demand side as well, and this is what's happening now on the distribution systems through these flexibility tenders. What's really important, and we know it's really clear that there's something the distribution networks hold very dear to themselves, is that this has to be done equitably. Everyone has to have the opportunity to engage with flexibility markets in the right way. It needs to be easy for people to contract flexibility services onto distribution networks. And it's really important that's done in a really open and transparent manner. So as I said here, the Energy Networks Open Networks project, which is essentially the trade body of the distribution and transmission companies in the UK, they've been tasked with delivering the Open Networks project, which is basically laying down the rules and regulations of flexibility trading, because it is really important. This is done in a really equitable and open way to make sure all people concerned with this have the opportunity to participate. Also worth mentioning the Energy Data Task Force as well, and I think they are funded by the Energy Catapult, which is run by the UK government. They've been taking a really close look at the retail energy market. Again, not perhaps a subject I want to talk too much about today, because we've all seen there's been some pretty seismic activity in the retail energy market over only the last couple of months. But the Energy Data Task Force have laid out the rules and regulations for how the retail energy market can basically be reformed. You know, they really believe that there's an opportunity for the users of the energy system to engage in entirely new ways. Lots of what the Energy Data Task Force are talking about is the value that we as users of energy, you know, the value that we can bring through some of this kind of flexibility trading. So there's a series of recommendations that the Energy Data Task Force has laid out, and again, I can't recommend it highly enough. So I think this is almost kind of the last slide from me, I believe, or the last but one at least before the summary. Again, this whole area of data and digitalization. We talked about the problems of renewable energy generation. We talked about the things we can do on the generation side. We've also touched on some of the technology solutions and the things we can do on the demand side. But we have to face the fact the owners and the operators of these networks are facing up to the fact that these networks were built in an analog age, I'll say. They are analog systems, basically. So we have a huge ecosystem of people who are concerned with what's happening on the electricity network. But one thing we are lacking at the moment is visibility of what's actually happening. And there is significant investment happening now in data and digitalization. And I mean, again, talking about data and digitalization, it's a bit like talking about smart grids the way we did 10 or 15 years ago. You know, the question's often asked, what does data and digitalization actually mean in terms of the way electricity networks are operated? And there's different ways to think about data and digitalization, but you know, perhaps it's fairly easy to say that what the network companies need is greater visibility. So there's a huge program now of installing sensors across assets to understand how assets are performing, how assets are aging, what circuit breakers are doing, what transformers are doing, how are cables operating. So we're beginning to see this emerging picture of what's actually happening on the network. You know, we can't take decisions about how to best optimize the way the network is used without that visibility of what's actually happening. There's an analogy that's quite widely used and quite often used. It's not, I didn't think of this, but we do see it often talked about. You can almost see the analogy with new business models such as Uber. The way networks have traditionally been run and developed has been like a local taxi company, where they have humans sat with two-way radios talking to other humans in cars and trying to work out, you know, humans relying on their intimate local geographic knowledge of where congestion might be and where taxi demand is likely to be. What we can see now with Uber is they've completely swept away that whole business model. You know, and Uber's business relies on having intimate knowledge of us, the users, of where their assets are in terms of the vehicles, you know, of how those vehicles are performing, of how long it takes vehicles to make journeys. You know, Uber have quite clearly demonstrated, as these other kind of, can we say, more modern types of business model like Netflix and some of the others, you know, they've understood that people are willing to pay for an enhanced service. So what we're now going through is some changes in the electricity transmission and distribution. We're beginning to see the emergence of these widespread sensors. We're beginning to see the emergence of this data. Beginning to get a lot greater visibility of how networks are performing. And what certainly the government believes, and I think it's fair to say we're all invested in, is that there's an ecosystem of people in between the assets, you know, that make up the electricity network and the people who use the electricity network. There's an ecosystem of really clever people, you know, and if we can put people in the right position in terms of giving them the data that they need, you know, then they are able to think up, you know, these new applications, new ways of using data, new ways of releasing value, and all that innovation is going to come from the markets as we go down this path of data and digitalization. Get this visibility of what's actually happening on the network to be able to let some of these new business models flourish and thrive, and let some of this new value be generated by you know, people who understand electricity, understand networks, understand data and digitalization, but you know, we can also bring some of these new really clever algorithms to bear. So that's kind of it from me. Hope that was okay. It was basically just briefly to recap. I think we talked about how the electricity network in the UK arrived where it is today, and how that is changing. And we talked about the global move to net zero and what that's going to mean in terms of the characteristics of some of the energy generation. And then I think just concluded by talking about the opportunities that we have for some of the new types of technology and the new ways of understanding and operating electricity networks. So I hope that was okay. Over to you, Bob, if you're still with us. I can see we have a number of questions in the chat.
Oh, Martin, sorry, Darren, get me so confused. That was brilliant. I really enjoyed that. I mean, it's good that this is going to be recorded, because I think there's enough content in there. You could listen to that presentation a few times to glean all the information that was in it. Just as for your information, we peaked at 400 attendees, and there are still 382 of our attendees out there. So that's had a really big impact.
Okay.
How do you want to do the questions, Darren? You can see them for yourself.
Yeah, I can see them now. Is my camera still on? I seem to have mixed up my screens, Bob.
I can see you. Perfect.
Okay, well, okay, then I can't see myself, but that's okay then, as long as I'm still present and correct. I don't know if, I mean, time is ticking on, Bob. I don't know what kind of time that we want to.
Well, I think the way I would look at it, you've talked solidly for close on an hour.
I know,
So I think
I've almost lost my voice.
Yes, indeed, and you've finished your drink as well into the bargain. So what I would suggest is if you could skim down and pick some of the sort of highlight questions.
Okay.
And then I think we've got to be grateful for what you've done for us this evening, which has been absolutely wonderful.
Okay. Well, here we go, about mentioning the reliability of the UK network. What are the metrics for this? We have something called the Interruptions and Incentives Scheme. This is for Alex Wood, 7:20. Basically, the distribution companies need to report each year how many interruptions they have for their network, both how many interruptions and the duration of those interruptions, the customer minutes lost, and customer interruptions, CIs and CMLs. So those numbers are reported every year into the regulator. What the regulator does is, based on a set of metrics, or based on the number of interruptions in any one year, the regulator then sets the company a target for the next year, an improvement target. And I don't, from memory, remember how much those CIs and CMLs are worth, but the amount of the amount of revenue that the companies can return to themselves is based on outperforming the regulatory contract, basically, and doing better than they did last year, because all networks are all slightly different. You have different urban locations, different rural locations, a different mix of urban density and rural locations. So the metrics are given to under the Interruptions and Incentive Scheme, reported to the regulator every year, and the companies enter the target for the next year for how to improve that. So Chris asked, a 20:7 frequency still controlled over an average as well as an instantaneous figure? No, Chris, it's an instantaneous figure over that 10-second time period that we talked about previously. So it's 24/7 instantaneous real-time balancing between supply and demand. And again, I hope I touched enough on the ancillary balancing services market in how the frequency is controlled. System strength, a major outage in 2010-2012. I think I remember this actually. I was at Electricity Northwest then. Yep, I remember that. Billingham was down for 3 hours. All power mobile were down. She's just wondering why the power was not rerouted by the southern links and why we're down so long. Well, I don't think that there is a challenge at the moment. This is for Tim, 7:20. There is a challenge at the moment. There's an awful lot of work happening with the National Grid. Now, it's in relation to the second point you've raised, Tim, about rerouting power. There is a congestion on the UK network now. What we're seeing is a huge amount of renewable energy in the north, but all the main demand is in the south. And you'd be surprised, there's only 2 or 3 lines that go and run north-south in the UK, so those lines are congested. So National Grid is busily now looking at some kind of innovative solution for how to reroute power, but it's not quite as simple as we might think. And the reason you were off for such a long time, Tim, is because again, these low frequency demand disconnect schemes that kicked in. Can't quite remember. I think there was 2 power stations. One was out for maintenance and one tripped out from memory, 2012, not that long ago. That was when, again, as I mentioned, in 2018, the low frequency demand disconnect schemes kicked in. Well, that was a similar experience then, that the distribution networks were disconnected basically automatically. They can't then reconnect because that will cause such a big spike in demand if they were all connected in one go. That would then cause the frequency to be dragged down. So to get those to recover from those low frequency demand disconnect events, what the distribution companies have to do is basically sectionalize their own networks and then bring them back section by section, so you don't get this big shock of demand. Alex is asking about 98.9% reliability. What would it take to reach 100%? I don't think it's possible, to be quite honest, Alex. That was 7:25. Many outages that happen today are due to people carrying out roadworks and digging up cables that are under the ground. You know, there are maps of cables under the ground, and any operator that takes a JCB to the earth in the UK is supposed to check first if there's cables underneath the ground, but that actually sometimes doesn't happen. We also, excuse me, have unfortunately, you know, people drive into electricity infrastructure, pavement mounted substations and boxes. So it would be difficult to achieve 100%. Although I know some countries in the world, I think out in the far north of Europe, where they don't tend to have so much overhead lines, they have much more underground networks. They have even higher, greater levels of reliability we do in the UK, because those underground networks are less susceptible to storm damage, wind, interference through third parties, or the range of other ways that the range of other innovative ways that people find to interfere with the electricity network. So I think that would be a big ask for the UK, and very expensive as well, I'd say.
Could I give you a little voice arrest for a moment?
Please.
I'd like to answer one of the questions, because it's something that's come up at a presentation just the other week, and it's one of the thing at the moment, and it's about electric vehicles, the Dave Sinclair. There's a man called Ian Cook who talks extensively on electric vehicles and how the batteries will be used in them, and it's almost inevitable that the batteries in vehicles will be a two-directional device. So at one point they will be taking power out of the network to recharge the battery, and at another point they will be pushing power back into the network. So as that becomes a bit like Darren saying about these smart systems come along, as the battery capacity in all these cars and trucks and whatever gets utilized, they actually become part of the story. And it may be that when you go home and plug your Nissan Leaf in, it actually is pushing power out into the system. And at 2 o'clock in the morning, when the wind's blowing high and they're trying to sink some of the power, it goes back into the cars. So I think the batteries in cars are seen as part of the network.
Yeah, absolutely.
As you come from Paul saying that's true. But what we're talking about, a bit like all these systems, what we see is the sort of version 1. These are the chargers will be in version 2, 3, 4. And I think that's a talk for another day, but those batteries will contribute. Darren, have you we can download these questions and we could answer them by email.
Okay, well, how about if I do that, because I'm feeling somewhat exhausted, Bob.
Well, that's what I thought. I'd give you a chance to give you a break. And I think we'll close with that. Thank you for the wonderful questions. Thanks for attending.
Yeah, it's been perfect. Just to
really enjoyable.
Bob, can I just also say and ask that I guess these slides that we've had today will be published on your website? Is that
what we'll do is, if all's worked well, and we've had one that didn't work well, your presentation and the slides will be all in the same video.
Okay. Well, what I'd like to do, though, Bob, is maybe try and publicise my email amongst the participants today. So if anyone does have any burning questions or would like to take the discussion further, I mean, you may be able to tell I'm quite enthusiastic about this subject, so I'm always happy to engage.
Darren, may I suggest that you yourself raise a question, and in the question put your email. If anybody's got a question, and that way we know that the Q&A is definitely caused. I'm not so sure about the chat.
Okay.
If you put a question before I end it, saying, if you've got a question, this is my email address, and we'll be able to do something with that.
Okay.
I think that's how it will work.
Yeah, okay. I will do that right now, Bob. I will do that before I shut down. Here we go. Yeah, I've got it. I can see it in the chat. Okay. Right. Well, thanks, Bob. Thanks for hosting. Thanks, everyone.
Well, thank you very much. Absolutely brilliant. I hope everybody enjoyed it.
It's my absolute pleasure. Thanks for being such a great audience, and I hope you all have a good rest of the evening. Thanks. Goodbye, folks.
Bye, Darren.
Goodbye.